Okay, so for this video, I want to go over problems that are called work rate problems. These are classic applications of rational equations, okay? So anytime you get to a unit on rational equations, you're pretty much guaranteed to see a work rate problem. Now, with work rate problems, you're assuming that individuals or machines are working at a constant rate of speed. Now, this is very realistic with machines. Not very realistic when you're dealing with people, humans, but we still make the assumption that whatever is working at a constant rate of speed. Now, the other assumption we have to make is that if it takes t units of time to complete a job, then 1 over t parts of the job would be complete in 1 hour. So consider a job that would take 4 hours to complete. If we're working at a constant rate of speed, we would assume that 1/4 of the job would be complete in 1 hour. So again, if it takes 4 hours of time to complete an entire job, working at a constant rate of speed, 1/4 of the job should be complete in 1 hour. So within these problems, what you're going to see is 2 individuals or 2 machines doing the same job. So what we do is we figure out the parts done by individual or machine A in 1 unit of time. We figure out the parts done by individual or machine B in 1 unit of time. And then we know or figure out how much time it would take working together, the machines or the people. And we figure out the parts done together in 1 unit of time. Now, this may not make sense, but let's say that there's a job and it takes individual A 4 hours. So that means 1/4 of the job would be complete in 1 hour. Let's say it takes individual B 5 hours to complete the job. Well, working at a constant rate of speed, 1/5 of the job would be done in 1 hour. We have no idea how long it takes these two if they work together. So let's say it takes them X hours. That means 1 over X parts of the job would be done in 1 hour if they worked together. This would create the equation that you would solve. So let's look at some examples. We're going to start with really easy examples where we're dealing with just numbers. And then I've got a couple of examples where we're going to have a little bit more algebra involved. Okay, so for our first example, we have that Layla can plant 1,000 seedlings in 2 hours. Lachlan, on the other hand, can plant 1,000 seedlings in 5 hours. How long would this job take if they worked together? Well, let's see what we have here. We know it takes Layla 2 hours. So that would mean that 1/2 of the job would be complete in 1 hour. Now for Lachlan, it took him a whopping 5 hours to do the job. So working at a constant rate of speed, which again, when you're dealing with humans, a constant rate of speed from start to finish is unlikely, but we still make that assumption. So Lachlan here in 1 hour should have completed 1/5 of the job. Now working together, we don't know how long it's going to take them. We're going to say X hours. So that means 1 over X parts of the job would be complete in 1 hour. So if we go back to that first slide, we want to now take our information for this problem and we want to create this type of equation. So we take the individual parts done by Layla, 1/2, the parts done by Lachlan, 1/5. Again, we're considering 1 unit of time. Our unit of time is hours. So in 1 hour, how much did Layla do? In 1 hour, how much did Lachlan do? And then in 1 hour, how much could we expect them to do together? Now you have got just a classic rational equation here. And you have to kind of remind yourself, okay, what do we do with rational equations? We find the LCD. So the LCD here is 10x. So what I do with that 10x is I take 10x and I multiply it by the entire rational equation. And for me personally, I like to show my work. And I multiply it individually by each term of the equation. I find I make fewer mistakes when I show my work on this step. Once you get really confident in what you're doing, you can sometimes do this in your head. I just encourage you to be really, really careful. It's easy to miss a piece. So you can always show your work if you need to. So we've multiplied all of the terms by the LCD. Now I want to do some simplifying. In the first term, 2 will go into the LCD of 10x 5 times. So I'm left with 5 times x times 1, or just 5x. In the second term, 5 will go into the LCD of 10x 2 times. So I'm left with 2 times x times 1, or 2x. And then finally, for the last term, the x's cancel, and I'm left with just 10 times 1, or 10. So now what I've done is I've taken this rational equation and I've converted it to something linear. So with linear equations, you want to get all of your variables together, your constants together, and then you do a little simple step to solve. So I want to combine like terms. 5x plus 2x is 7x. 7x equals 10. I then divide by 7. That gets me x alone, and you've got options on how you write your answer. You could certainly write your answer as 10 over 7, but generally speaking, when we're dealing with word problems, improper fractions aren't going to be your best bet. So what you could do is either write your answer as a decimal or as a mixed number. Now, if I take 10 and divide it by 7, I get 1.428571429. That's not a very nice answer, so instead, I'm going to write this as a mixed number. So how many times will 7 go into 10? It will go in 1 time with 3 left over. So if Layla and Lachlan worked together, they could plant 1,000 seedlings in 1 3/7 hours. All right. Now, even though Lachlan is much, much slower than Layla, he still is going to speed her up. So the time working together is still going to be less than each individual time. All right. Let's look at another similar example. So in this one, we have 2 kids shoveling a driveway. We have that Lanen can shovel the driveway in 3 hours. Gage, on the other hand, can shovel the same driveway in 6 hours. How long would it take Lanen and Gage if they worked together? So let's see. Lanen takes 3 hours. So working at a constant rate of speed, we would assume 1/3 of the job would be complete in 1 hour. Gage takes 6 hours. So we would assume that 1/6 of the job would be complete in 1 hour. Now, whoops. Working together, we don't know how long it's going to take them. We'll just say X hours. So in 1 hour, 1 over X parts of the job should be complete. So my equation is going to be Lanen plus Gage, the parts of the job they could complete in 1 hour, and that's going to equal the parts of the job they could complete working together. Now, for this example, or this equation, we have an LCD of 6. Whoops, I used a T and not an X. Let me use. I need to be consistent. So that's an X and that's an X. All right, so I'm going to take each individual term in this equation and I'm going to multiply it by the LCD. All right, and then I'm going to simplify. So in the first term, 3 goes into 6 twice, leaving 2 times x times 1, or just 2x. In the second term, the 6's cancel, so I'm just left with 1 times x, or x. In the third and last term, the x's actually cancel, and I'm left with just 6 times 1. So again, I did a little work. I've got a linear equation to solve, so I get 3x equals 6. I want to solve for x, and I get x equals 2. So if we go back, x was the number of hours it would take Lanen and Gage working together. So we would say x equals 2 hours if these two work together. So again, even though Gage is much, much slower than Lanen, working with Lanen, it's still going to be less time than it would take Lanen working alone. All right, let's look at another example. So this example is slightly different. In this case, we don't know both individual times. We know one individual time and we know the time working together. All right, so our goal in this case is to find the other missing individual time. So we have that Ina can cut grass in 3 hours. Working with Lorelei, they can cut grass in 2 hours. How long would it take Lorelei to do the job working alone? Well, Ina, we know, can do the job in 3 hours. So in 1 hour, 1/3 of the job should be complete. Now, Lorelei, we don't know how long it's going to take her. So we're going to say it's going to take her X hours. So that means in 1 hour, 1 over X parts of the job should be complete. Now, whoops, I did it again. Now, working together, we're told it takes 2 hours. So that means in 1 hour, 1/2 of the job should be complete if Lorelei and Ina work together. So we take the individual times or the individual parts per hour, and we add those and set it equal to the together parts per hour. So in this case, just like the previous example, we have an LCD of 6x. I'm going to take each term and multiply it by 6x. I keep thinking with practice I'll get better at writing on this board, but I don't, so it's still sloppy. All right, so we've multiplied each term by the LCD. We want to start canceling. So this 3 goes into 6 twice, so I'm left with 2 times x times 1, or just 2x. For the middle term, the x's cancel, so I'm left with just 6 times 1, or 6. In the third and last term, 2 goes into 6 3 times. I'm left with 3 times x times 1, or 3x. So again, with a little bit of work, we converted our rational equation to something linear. I want to solve for x. I do that by getting my x's together. So I get 6 equals x. And what this means is x equals 6 hours if Lorelei works alone. All right. Ooh, that got a little messy. All right, so Enid can cut the grass in 3 hours. If she works with Lorelei, it takes 2 hours. But if Lorelei works all by herself, it's going to take her a whopping 6 hours to cut the grass. So this is actually exactly like the previous example. We just had a different missing piece. Let's look at another example. All right. So again, in this case, we're going to have one individual time. We're going to know the time together. We're going to look for the other individual time. So Jeremy can paint a 1,500 square foot apartment in 20 hours. If he works with Haley, the job takes only 12 hours. How long would it take Haley to complete the job if she worked alone? So let's see. I keep laying my hand on the screen and it's making a problem. All right, so Jeremy, it's going to take him 20 hours. If he works at a constant rate of speed, 1/20th of the job should be complete in 1 hour. Haley, we don't know how long it's going to take her, so we're going to say x hours. Again, working at a constant rate of speed, 1 over x parts of the job should be complete in an hour. Working together, we know it only takes them 12 hours. So in 1 hour, 1/12th of the job should be complete. So we take the individual parts of the job completed in an hour, set it equal to the parts of the job completed if they work together. We find an LCD. So this one might not be as obvious, but it's going to be 60x. So I take 60x and I multiply it by each term in the equation. And then I simplify. So 20 will go into 63 times. So I'm left with 3 times x times 1. In the second term, the x's cancel. So I'm left with 60 times 1. And then in the last term, 12 will go into 65 times. So I'm left with 5 times x times 1, or 5x. So I want to go ahead and solve for x. This is now a linear equation. So I want to move my x's, get them together. So I get 60 equals 2x. I divide by 2. And I get that x equals 30 hours if, now remember, x in this case was Haley. All right. So this is 30 hours if Haley works alone. All right. So again, you take the individual parts per hour, add those up, set it equal to the together parts per hour, and then you just solve your rational equation. Now, there are some examples where you have more algebra involved, and this is a good example here. So we have a canned soup factory has an old canning machine. They decide to add a new machine that works twice as fast. With both machines, 10,000 cans of soup can be produced in 6 hours. How long would it take the new machine to produce 10,000 cans of soup? So we have the old machine and we have the new machine, and we've got to figure out a little bit before we even start setting up our equation. Now, the new machine can work twice as fast as the old machine, and this is an easy mistake to make. I've made it many times in my life. So we're talking hours here. So if the old machine can do the job in X hours, we want half that time for the new machine because the new machine works twice as fast. Okay, so this is kind of a trippy thing. So let's say the new machine can do the job in 2 hours. That means it's going to take the old machine twice as long. So I'm going to say the new machine is X, the old machine is 2X. So you got to be really careful with an example like this. I made this very mistake just last night, okay? So you don't want to say the old machine is X and the new machine is 2X because the new machine works twice as fast. So it takes half the amount of time that the old machine takes, okay? And then working together, we know that the job we're looking at here is 10,000 cans of soup. So that's kind of the job that needs to be completed. And working together, these two machines would take 6 hours to complete the 10,000 cans of soup. So in 1 hour, how much of the job is complete for each of these? Well, 1 over 2x parts of the job would be complete in 1 hour for the old machine. 1 over x parts of the job would be complete for the new machine. And 1 over 6 parts of the job would be complete if the two machines work together. Let me fix that. That looks ugly. So we're going to get 1 over 2x plus 1 over x equals 1 over 6. The LCD here is 6x. So I get 6x times 1 over 2x plus 6x times 1 over x. And that's going to equal 6x times 1 over 6. So we want to start canceling. In the first term, 2 goes into 6 3 times, and the x's cancel. So I'm just left with 3 times 1. In the second term, the x's cancel, and I'm left with 6 times 1. And then in the third term, the 6's cancel, and I'm left with just x times 1. So basically, we get x equals 9 hours. Now, you have to ask yourself, what was x? Well, x was the hours for the new machine, right? So it takes 9 hours if the new machine works alone. Now, with that said, knowing that the old machine takes twice as long, how long would it take the new machine, or the old machine rather, to produce 10,000 cans of soup? It would take it 18 hours. So with problems like this, just make sure you're answering the question that was asked. The question was, how many hours would it take the new machine working alone? It would take it 9 hours. And that's it. All right. One more example. So in this example, we have 2 people doing dishes. So working alone, Eli takes 5 minutes longer to wash dishes than it takes Fred when he works alone. Washing dishes together, Fred and Eli can finish the job in just 6 minutes. How long does it take Eli to wash the dishes working by himself? So let's do a little work here. Now, we know that Eli takes 5 minutes longer to wash the dishes than it takes Fred. So let's say Fred takes X minutes. That means it's going to take Eli X plus 5 minutes. And then working together, we get 6 minutes. So parts completed per minute, 1 over X plus 5. Parts of the job would be completed in 1 minute for Eli. 1 over X parts of the job would be completed in 1 minute for Fred. And 1 over 6 parts of the job would be completed in 1 minute if they work together. So we have 1 over X plus 5 plus 1 over X equals 1 over 6. Now the LCD in this case is going to be 6x times x plus 5. This is going to be a little bit, it's not harder to solve, but there's a little bit more involved in solving this one. Okay. So if I take each term, and I'm going to try to go ahead and show this, I hope I have enough room. I'm going to take each term and multiply it by the LCD. I forgot my plus sign. I think I can fit it. Darn it. I keep accidentally touching the screen. All right, so you definitely don't have to show this step where you multiply everything by the LCD, but it's a good step if you're feeling a little unsure of yourself, or if you're not, if you're still making little mistakes, show this step. All right, you can do it in your head, just be cautious. All right, so I'm going to start canceling. In the first term, x plus 5 cancels x plus 5, and I'm left with 6x times 1. In the second term, the x's cancel, and I'm left with 6 times 1 times x plus 5. And then in the third term, the 6's cancel, and I'm left with x times x plus 5. We're going to do some simplifying. So I get 6x plus 6x plus 30 equals x squared plus 5x. All right. So I get 12x plus 30 equals x squared plus 5x. We definitely have something quadratic. The x squared tells us that. And what you want to do anytime you're solving a quadratic equation is you want to set it equal to 0. You want to put it in standard form, and you want to make sure your quadratic or your squared term stays positive. So I'm going to move 12x and 30. So I get 0 equals x squared minus 7x minus 30. And so basically we want to try to factor this quadratic, okay? So I want to find factors of negative 30 that would add to negative 7. And it just so happens that if I have x minus 10 and x plus 3, well, negative 10 and 3 equal my negative 30, but negative 10 plus 3 equal my negative 7, all right? So what you do at this point is you take each of these terms, you set them equal to 0. So I'm going to have to go over here. Well, I can do it over here. So x minus 10 equals 0. So that tells me x is 10. X plus 3 equals 0. So that tells me x is negative 3. Now, you have to think about this. We've got two answers, and one of them just doesn't make sense. So if we go back and figure out what x is the number of minutes it takes it takes Fred working alone. Could Fred do the job of washing dishes in negative 3 minutes? Of course not. This doesn't make sense. This does. Okay. So x equals 10 minutes. And then if we want to look at Eli right here, x plus 5 equals 15 minutes. So that means Fred can do the job in 10 minutes. Eli can do the job in 15 minutes. And we just want to make sure we look to see what the question is asking. The question is asking, how long does it take Eli to wash the dishes by himself? So our answer would be 15 minutes for Eli working alone. And there you have it. Make sure you answer the question that is being asked, okay? So we looked at several examples. Just to do a quick recap. Work rate problems, you assume individuals or machines are working at a constant rate. Again, assuming that constant rate, if it takes t units of time to complete the job, then 1 over t parts of the job would be complete in 1 unit of time. So the example I gave you all is if a job takes 4 hours, 1/4 of the job should be complete in 1 hour, assuming this constant rate of speed. So what you do is you're generally going to have 2 machines or 2 people. You figure out the parts done in 1 unit of time by individual A. You add that to the parts done in 1 unit of time by individual B, and you set that equal to the parts done in 1 unit of time if these individuals work together. All right, we looked at a couple of examples where we knew the individual times. We did not know the time working together, so we set up an equation and found that. We looked at a couple of examples where we didn't know both individual times. We knew one individual time and we knew the time working together, and we had to find the second individual time. And then we looked at a couple of examples where we had a little more algebra involved. So the initial times for the individuals, you had to use direct translation to find an expression to represent the individual time for the machines or the people, and then you could use that to create your rational equation. Okay, so that's work rate problems. Be really careful, like I said in that one example with the canning machines, one machine works twice as fast. So if machine 1 takes 5 hours and the other machine is twice as fast, that means it does the job in half the time. So if the old machine, we were talking about the soup machines, if the old machine takes 5 hours, the new machine only takes 2.5 hours. So be really careful with the algebra. Like I said, I made a mistake like that just last night. All right, so that's work rate problems. Make sure you know how to solve rational equations before you start these problems. All right, best of luck.